Now we're going to look at a slightly different topic related to regression. We're going to look at some of these assumptions of regression. There are several assumptions relevant in particular for hypothesis testing. First, we're assuming that the relationship between the input or predictor variable x and our outcome is linear in the population. Just like correlation, linear regression only captures linear relationships. Number two, we're assuming that the standard deviation of the outcome variable is the same for all values of the input variable in the population. Point three, we're assuming that the outcome variable is normally distributed around the population regression line. These are assumptions about the population. We never truly know whether these assumptions hold, whether these characteristics hold in the population, but often we can check the data, the sample of data, as suggestions whether or not these are met. If our data set, if our sample of data, if we really think that they don't accord with these assumptions, we might be more concerned about assuming these aspects of the population. But again, this is just a random sample of data, so we never fully know whether or not these assumptions are holding until or unless we conduct a census, unless we have the entire population on hand. This process of checking model fit, of considering the assumptions of regression, this whole process is called regression diagnostics. It's a very important part of regression. The idea is that we want to just kind of check out the model. Does it make sense? Do we think that it's really fitting onto a linear relationship? Right? So there are a few basic diagnostic checks we can conduct. First, the assumption is that the relationship between the input variable x and the outcome variable y is linear in the population. Well, what we can do is, based on the sample of data, we can check a scatter plot between x and y. Right? If our sample data, if it's highly nonlinear, right, we might be a little bit concerned about making that assumption in the population. The second assumption is that the standard deviation of the outcome is the same for all values of the input variable in the population. So again, we can check with the scatter plot between the residuals and x. Again, we're checking based on the sample of data. Right? We don't know what the population is doing, but if our sample is suggesting that the standard deviation outcome is not the same for all values of the input variable, then we might be more reluctant to make that assumption about the population. For number three, we're assuming that the outcome variable is normally distributed, right? It's kind of mound-shaped and symmetric around the population regression line. What we can do is we can check with a histogram of the residuals of the errors overlaid with a normal distribution model. This is based on the sample of data. Right? And we'll go through a few of these. So in our example, in which we're looking at population growth as a predictor for life expectancy across a sample of countries, we might say, well, is the relationship between x and y linear? Now this is a sample of data, we're treating it as a sample of data. Is that linear? Well, it's roughly linear, okay? And this is approximate, but it's roughly linear. You do have an outlier at the very bottom there, but it's approximately linear. It's not obviously U-shaped, for example. We might say, well, is the standard deviation of the outcome the same for all values of x? So what you do is you can see here, we go across our x variable, right, and then we're just looking at the standard deviation of the outcome variable, and we see, ignoring that outlier of Haiti, the spread above and below the mean for different values of x is roughly the same, roughly. Then we might say, well, is the outcome normally distributed around that regression line? So, we're just looking at the residuals around the regression line. Is the outcome normally distributed? More or less, but you can see we also have that outlier of Haiti. That one bin is holding that Haiti outlier, but it's roughly normal. Okay, you can see the normal distribution model is overlaid on this histogram. Right? Again, this is approximate. Right? This is where statistics, it's not necessarily a right or wrong answer. We're just trying to look at the sample data to check these assumptions. These assumptions are made about the population. We look at our sample of data. We say, well, it looks like the sample of data roughly approximate these assumptions about the population, so we're not going to be too concerned about making these kinds of assumptions. Now, what do you do if you think these assumptions are possibly violated, right, through these diagnostic plots? There are typically two common solutions. First, people often do nonlinear transformations. Earlier we talked about nonlinear transformations, such as a logarithm. The idea is that even though linear regression assumes a linear relationship between x and y, the great thing about a nonlinear relationship, because since you're changing the shape of the distribution of these numerical variables, you can make a nonlinear relationship, sort of an upside down U, for example, you can kind of straighten it out, kind of like when you take a coat hanger and you kind of straighten out that coat hanger. That's what a nonlinear transformation does. So often, this is why simple linear regression or linear regression models in general are actually quite flexible models, because you can shape the data in many different ways so that a nonlinear relationship can look linear and appear linear and is transformed into a linear way, and then you can fit your linear regression model. So just check. Maybe you can conduct a nonlinear transformation. For example, in public health, especially in cross-national studies, when you're comparing different countries, people often apply a logarithmic transformation to population data, to population growth, or the population of different countries. That's because the population of different countries is really not linear. You have a couple countries with huge populations, like China or Russia, and then lots of countries with sort of middle-level populations of 10 million, 5 million. So in order to straighten that out, you might want to apply a nonlinear transformation, such as a logarithmic transformation. Another and related solution is to remove outliers. The idea is that you might want to remove any potential outlying value in either x or y, and that can improve the model fit. For example, in this case, we have Haiti, which is an outlier. So we might consider removing Haiti. So let's look at our results of life expectancy after we've removed Haiti from the analysis. Right? Here we have the intercept and slope. Right? The p-values are roughly the same, but now the slope for the coefficient is negative 1.873 instead of negative 2.198. This suggests that this Haiti as an outlier was having a particularly large influence on the regression slope. Right? It was perhaps exaggerating this relationship between population growth and life expectancy. This is what the scatter plot looks like after we have removed Haiti from the analysis. When we look through the diagnostic charts, is the relationship between x and y linear? Well, it looks a little bit more linear now that we've removed Haiti. Is the relationship in terms of the standard deviation of the outcome, is it the same for all values of x? So we take each of these values of x and we're checking the standard deviation of the outcome. After we have removed Haiti, you can see that the spread above and below the line is roughly the same for the different values of x. Looks a little bit better without Haiti there. And then what I say is the outcome normally distributed around the regression line. So now that we moved Haiti, the distribution is much more symmetric and is a better approximation in terms of the normal distribution model. So we can say that residuals are approximately normally distributed. So a few things to know at this point. We can conduct inferences on the intercept and slope of a regression model fit to a sample of data. The idea behind it is that we have a sample of data, we fit a regression model to that sample of data, and we want to say something about an unknown population. Right? What is the intercept and slope in a population? And assuming that the sample is randomly sampled from that population, we can conduct these kinds of inferences. We're going to focus on using statistical software to obtain t-ratios, otherwise known as t-values or t-test statistics, p-values, and confidence intervals. And regression has several assumptions entailing about the population. So these assumptions, we can use various diagnostic plots to look for potential violations of these assumptions, but we never fully know whether these assumptions are met unless we actually obtain the entire population data. And with that, we conclude our discussion of inferences for regression.